Good afternoon, ladies and gentlemen. We welcome you today to our webinar on efficiency and NVH simulations for transmissions. As you've read in our announcements, we'll be talking today about the electrification of vehicles and increased demands on overall efficiency that are driving a wide spectrum of new transmission concepts. Major market drivers include more and more stringent legal requirements as well as increased focus on real-world driving conditions. NVH engineers are challenged to optimize the acoustic behavior of vehicles while keeping an eye on emissions regulations and efficiency targets. This webinar will introduce you to AVL's simulation approach to master these challenges. So we'd like to thank you all for being here and welcome. Gear Technology Magazine, the Journal of Gear Manufacturing, is proud to present another in a series of educational webinars for the gear industry. Today's webinar is presented by AVL, the world's largest independent company for the development of powertrain systems with internal combustion engines, as well as instrumentation and test systems. We'll be just starting in a moment here as we gather our attendees together. I'd like to welcome everybody. My name is Gary Jesch, and I'm with Gear Technology Magazine, and I'll be your moderator and host today. And on our presentation panel, we have Christoph Schweiger, a team leader of structural dynamics simulation. He's been with AVL for 19 years. His focus is on NVH, strength and durability, and tribology regarding engine, transmission, and drivelines with focus on the entire real-world driving conditions. His presentation, our first one, is about transmission NVH rattle and whine. Borislav Karlin, our second presenter, is an R&D Project Manager and has been with AVL for 22 years. Over the past 3 years, Karlin's primary area of responsibility has been methodology development for NVH and durability topics on engine, transmission, and driveline. His presentation covers transmission efficiency simulation. So we turn first to Christoph Schweiger, And Christoph, we're looking forward to your presentation. I believe we're ready to go. I would just remind our audience that we are accepting questions of our presenters. If you'd like to use your GoToWebinar control panel, you'll see a tab marked questions in there, and feel free to type in a question during the presentation, and if you'd like, or when the two gentlemen are finished with their talks. And we're more than happy to address these questions in the time left available to us. I will be continuing right up to the top of the hour. So once again, welcome to everybody. We're glad to have you here. And Mr. Schweiger, I think we're ready for you to begin if you'd like.
Yeah, thank you very much, Gary. Very welcome to all of you participating the webinar. The first topic, as Gary already said, will be about transmission NVH, where we especially focus on gear rattle and gear whine as one of the most important gear noises in the transmissions. First of all, I want to just sketch the application area, what we can use, what we can deal with. It depends. So we have one methodology which can be applied on different types of transmissions. This can be rather simple transmissions, automotive transmission for sure. It can be manual transmission, automatic transmission, double clutch transmission, constant velocity transmissions. And for sure, the electrification as well is also important. Challenging transmissions. Tractor transmission are probably one of the most complex transmissions, which can be where we can deal with those as well. Very important upcoming is transmission for electric drive. So especially gear whine is very important on this topic, on these transmissions. As there is a less masking noise on that, but also rear axles noise. We can deal with that as well, especially go for whine orders. coming out of the final drive, and also the rear wheel transmissions as well. But not only automotive applications can be covered with our approach. It can be also industrial transmissions, like in wind turbines, in, for example, grinding mills, so very heavy industrial transmissions. Also trains can be covered. Train bogies, there are also transmission coming from the electrical engine down to the wheel. We're also noise getting more and more important. And last but not least, also airplanes transmission, especially coming from the turbine going to the propeller, typically very complex transmissions are necessary. And here with our approach, we can deal with all the flexibilities in the system on the housing, which is especially here very, very important. But basically, that's our approach. So in the end of the day, NVH or a noise starts with some kind of excitation, which we can see here. We have any variant excitation, which is typically inside the gear mesh. This needs to be transferred somehow to the housing, and which excite the housing, and the housing starts vibrating, which in the end of the day results in a response, and response is the noise we can hear, and this is important for 2 points. It's an objective assessment for legislation, for example. So pass-by noises getting much more important in next month, I would say, especially for trucks, let's say. And the second one for sure is a subjective assessment, which goes in the direction of branding of the noise design, of the NVH design. So this is a very subjective topic, and yeah, topics like sound design, quality, annoying, sporty, pleasant, subjects are placed on that and can be designed with the tool. For sure, there is always a certain trade-off. Nothing is for free. So when dealing with transmission, there might be trade-offs with the performance. There will be trade-offs with fuel consumptions, and then fuel consumption for sure is directly connected to emissions. Temperature, thermal management, big topic for sure. Packaging weight, durability, costs, and just one example that this gets a better picture on that. Oil level is good because it reduces the rattle, and we'll come to that in more detail later. But for sure, if you have a higher oil level inside the transmission, this is very bad for the efficiency. So this is let's say very clear trade-off, which has to be considered and analyzed in detail with those tools. So maybe a little bit less abstract. What's the acoustic function chain? So we have a gearbox here, right here. We have a housing, we have the internals, we have the gears, and we have any kind of excitation. So it can be whine, can be rattle, whatever, yeah. So it happens inside the gear mesh, and this needs to be transferred somehow to the housing, because if there is inside the gearbox any kind of noise, typically nobody cares of. But the problem is it's transferred via the shafts to the bearings to the housing. So that means we have to consider also the transfer path within the simulation. So we have to consider the bearings and the flexible shafts as well in the end, to get the right amount of force excitation to the transmission housing. For sure, these forces which are applied on the structure will excite some structural modes and gives a structural response. We can, for just this example here, we have this cover here. This is rather red, so this high vibrational area, which in the end radiates into the free field for the airborne noise. And this is the fourth point, the noise radiation. So again, it's a transfer coming from the housing, from the structure to the airborne noise, which can be covered as well. Typically, acoustic assessment is somehow done going on the airborne noise. Just an example here, we can see here in this Campbell diagram the sound pressure level shown. Very typical for the gear rattle, we can see in the lower frequently wide band excitations in a certain speeds, and we have the very clear whine orders, this tonal noise of whine. So could be one order, could be two orders, three orders, depends on the gear mesh itself and on the transmission itself. But these are the typical results which needs to be addressed and which needs to be optimized in the relevant system by variation. So you can reduce rattle with different friction or clearances or torsional vibrations, and whine with changing microgeometries and so on. So in the end, it should be there is a predictive method which covers the detailed physics. So from the excitation over the transfer to the housing, excitation of the housing, and so the entire NVH generation process is covered within this approach. I want to go a little bit to detail about the gear rattle right now. So the gear rattle, it's repeated impacts which typically come up for loose gears. So we have loose gears, they're impacting and backlash and driving flank. It's a short and let's say moderate impact, let's say. What's the important drivers on that? The important driver is the torque fluctuation. So we always need some kind of a speed irregularity on it, for sure coming up of IC engines. So also IC engines and torque insulation is an important topic on that. And for sure we have this excitation and in the end of the day on the housing. You can see here just an example how this may look like. We have the contact forces on the left side, so on the driving flank, on the right side on the backlash flank. So we have these contact forces, and for sure this gives a certain excitation to the housing, and this transferred to here. A little bit more in detail. What we need for rattle, it's we have to have some speed irregularity. So we have an angular acceleration, and we have a drag torque and the inertia. If this goes together, if the drag torque is very large, there's always a contact on one side. If the drag torque is low and the inertia is rather low, then we come to the point that we get changing contact flanks, and these are exactly the impacts we have. What we have to consider in detail while calculating the rattle excitation, what we need to have a gear contact model, which really includes the backlash to get the energy into the system. For sure, very important is damping. So there is also an EHL damping approach inside our gear model, which covers the amount of oil between the flanks. As I already said, also important is the drag torque, and one of the let's say most important drag torques generated beside all bearings and seals and so on, for sure, is the oil resistance coming out of the oil splash, which can be considered with another tool, with AVL Fire, which is a 3D CFD code. About the transfer, so we have now a certain excitation done, and it happens within the gear. So we have to transfer the forces to the housing, and this is done via flexible shafts. They can be fan-based, can be more simplified, can be structured models. We have rather detailed bearing models inside here, which are basically designed for the acoustic transfer path, for the force transfer. They can consider friction as well, as we need it for the right drag torque. And with this, we go for the housing, with the flexible housing, which can vibrate in the end of the day and gives us the response we already have discussed. On the other side, we have the torque fluctuation. Torque fluctuation comes from AC engine, as I already said, and there is a certain possibility to give a certain torque insulation on that. So there could be clutches, torque converter, dual mass flywheels, pendulum dampers. And basically, this is also a functionality which is inside the software. So you can couple also the AC engine with the transmission, calculate at the same time, and they can be cover the entire angular acceleration. So there's speed irregularity at the input of the transmission as a very important source. Basically, with this system, with these considerations, this will end up in this typically rattle excitation or rattle response plots. You can see here that's a microphone, so it's an airborne noise result with this classically wideband excitations on the structure. And here we can see it's a typically wavelet spectrum. So we have an impact and we have the decay, and this is a single event, and this happens all the time. Can be periodic, can be non-periodic, depends on the system. This is how a rattle looks like and how it's propagated to the housing and finally to the airborne noise. I already mentioned it a little bit. One important thing is the drag torque of the loose gears acting with the oil and the oil mist to produce additional losses, and this will be added to the drag torque. And this is rather important for the gear rattle, and this can be calculated in detail and used as a map. So it's not a code simulation, as a map inside Evelyn side in the tool, which is the multi-body dynamic system to calculate the rattle. The other important noise effect is the gear whine. Gear whine, which comes up with its tonality, which is typically quite an annoying noise. You can see it here as an example. It's just only this one order going in the noise, and it's very much higher than the background noise. So it is, can be heard very good, and it's assumed as felt as annoying. Typically, or it's necessary that this is a loaded gear. Opposite to gear rattle, where it's typically loose parts. So the loaded gear, we have a torque flow going here. So we have here the possibility of gear whine as well as for the final drive. Basically, this comes out of periodic fluctuations in the gear mesh. Basically known as a transmission error. Maybe that's a little bit more clear. This may come out of geometric insufficiencies, so manufacturing inaccuracies, tolerances, runouts, bending, shaft bending, however. And there can be elastic deflections under load, and which is increasing the transmission error. And basically this is comes up as a narrow banded tonal noise in the meshing frequencies, and for sure in its harmonics and also modulations. So we can see here, just an example, a meshing stiffness number depending on number of teeth in contact, and for sure there is this change of the stiffness exactly gives a certain excitation. You can see it in here, just an example, there is ideal rotating gear mesh, but we can easily see the different deformations, the different contact forces, and this is exactly transferred to the shafts, and the shafts transfer this again to the housing and excite the housing. As I already said, the main root cause of this is the gear mesh itself, and it's influenced by the macrogeometry and the microgeometry of the gear mesh. That's quite important. It's caused by periodic fluctuations of the gears. So, for example, with multiple gear contact, with a single gear contact, this already gives us a certain impact on the gear stiffness. it's a variable meshing stiffness, and exactly this is what we have to consider in detail, as well as the elastic deflections under load. So we have to consider the load as well. What we need for wine, what we consider for the gear wine calculation, so we have to consider the we have to calculate and consider the contact force in the gear mesh itself for the gear wine, and for this we need to have a 3D multi-flag contact model, which brings into contact the real profiles. With this, we are capable to consider tooth corrections and modifications, because if we have a banded system, a banded shaft, a flexible shaft under load, we will have a certain inclinations, and together with tooth corrections and modifications, for sure we can reduce the change of the stiffness and the change of the impact forces, the contact forces, which reduces wine. The transfer path going through the shafts, through the bearing, to the housing is covered again in a similar way. It's the same model, so we can calculate gear rattle and gear wine in the same model and the same time. We can consider the change of backlashes of the and the change of the contact point because of the misaligned or inclined shafts. Just an example how this may look like. We have here a certain edge loading because of a bending of a shaft. We can see we have a very high change of the forces right here on the edge. With a certain lead crowning, already this effect can be reduced. And this is shown here. In addition to that, we can consider a full flexible gear wheel body as well, based on FEM bodies. So if you have a very sophisticated gear wheel design, which is typically not covered, this can be used as a FEM body as well. So there is more or less no limit on the design of the gear wheel to predict the stiffness of the gear as well as the transfer path from the gear to the gear shaft. Just one example how the entire process works. We have here a gearbox, the third gear engaged, the 36 teeth on the first gear, running on 3000. So we have here the engine. We have a second order coming from the SC engine. We have a 36th order, which is a dead speed 1800 hertz. We also can see the modulated frequencies, so 36 order minus second order plus second order, which comes out of the torque variation. Oh, that's the sidebands we are generating. So this is already inside the model. If we go for sound radiation on that, you can see on the input power very clear this whine order of this gear mesh. And this is also as a response on the microphone positions visible, very good. And in the 3D field shows it very well. It's a very tonal noise. There is almost no covering of the background noise. So this is really annoying, and you can see the impact of the gear whine directly here in this field. So that's the airborne noises, the sound pressure level can be indicated on that, and this is really huge difference, and this is what describes the tonality of this system. Just one more example with the entire chain going really from considering the gear mesh up to the microphones. There is also a possibility to define an arbitrary variable contact stiffness instead of calculating it internally based on the gear mesh itself. So it's just another type of definition, but sometimes this could be useful. What's the impact? The question on this is, what's the impact of the change of the stiffness? So we have here a base stiffness having a certain change of the stiffness, a variable contact stiffness, and we have a modified stiffness. However, this is done, yeah. And the question is for sure, what's the impact of this to the airborne noise? You can evaluate this in bearing forces, and for sure this is can be seen, but sometimes a little bit difficult to judge. Is 18 newtons bad, or is it already good? Going up to the airborne noise, this tells you absolute values. So the increase or the change, the influence on this contact stiffness gives you in the wine order 60 dB, which can be seen here in this frequency plot, in this order plot, and also in the Camper diagram. We can see here there is a huge, much higher amplitudes than here, and 60 dB is already a number. There is a certain feeling available what this really means. Yeah, and I'm already at the end of my presentation. Thank you very much for listening.
Thank you, Christoph. Very nicely done. The graphics on your slideshow were just excellent. It really helps clear things up to be able to see so much about how this looks visually as well as how it sounds. So thank you very much. We're turning now to Borislav Karlin, who is our next presenter. As I said, Borislav is an R&D project manager, and his presentation coming up is about transmission efficiency simulation. And we are receiving some questions. We will be answering questions after Borislav has completed his part in this. And so I guess, Borislav, we're ready for you. Are you showing your slides now?
Yes, thank you, Gary, for introduction. Christoph for excellent presentation. So I will now, if you everybody look, can see my screen, I will go with presentation about transmission efficiency simulation. So in the first part of this presentation, I will give just a short introduction about different simulation topics in transmission efficiency simulation and overall process in powertrain development. Then we will go with the topic with detailed explanation how transmission friction and other losses are considered in simulation tools. And finally, I will show also one case study where how we used transmission efficiency results in a real process and real project. So when we are talking about system, about simulation methodology in vehicle development, so we can distinguish two different groups of simulation tools. So the first one is are simulation tools used for system calculation. So and those tools are dealing with very high complexity level, so that we have all parts and all components of complex vehicle included in this simulation. Of course, with some simplification which are necessary in this case. Typical approach and the results of such simulation are calculation of fuel consumption, CO2 emission, energy management in vehicle, and so on. The mathematical model used here for prediction of friction are quite simplified because system level which is used in this case. If we want to look in the details where friction losses are generated, so we are going in opposite direction. So from drive cycle domain to component domain, where we are using complex mathematical models to predict the local behavior like deformation, flow, failure mechanisms of different components and also different subsystems. In current approach, these two approaches are quite uncoupled and not well connected in a whole development process. So our intention in this work is to avoid this isolation between two simulation methodologies and to make coupling as much as possible between these two approaches. If you look at the same simulation tools, but from the view of a development process, showed illustrated here as a classical V process. So we are starting by office simulation, looking first on the system design, then going in details with component design, and finally going with real hardware development and full system integration. When we are looking left branch of the V process, so we don't want just to sequentially execute a different task in this process, but we want to make that system tools use results from subsystem simulation to improve accuracy and reliability of these results. So this is especially important when we are going on the right side of the V process, where we coupling the simulation tools with real hardware, even it is with the hardware in the loop approach or software in the loop approach, and where we need really accurate system simulation. Going then for the overall efficiency prediction of complete vehicle, so we for sure need to consider also friction in which is generated in engine, in internal classically in internal combustion engine. In this case, if you look for the results of friction strip down test, we can see that the majority of mechanical friction losses is generated by lubricated contacts. And 30% of them is generated by piston group, 25% like illustrated here by crankshaft main bearings. And to accurately consider this in simulation, we developed the advanced approach in multi-body simulation with detailed electrohydrodynamic contact model which is used, which considers fully mixed lubrication conditions, and this mathematical model is can be used for analyzing of piston to liner contact issues and also sliding conditions in slider bearings, as well as also contact conditions in axial thrust bearings. The next in conventional or and also in hybrid transmission, or even just in electrified powertrain, we have transmission as a source of main source of power losses. If you look for the power losses in transmission, so we can divide them in two main groups. So first one, shown here in the blue square, is the mechanical losses in transmission. So when we look for the mechanical losses, so different mechanical components generate friction losses like gears, bearings, clutches, or oil pumps, sealings, or synchronizer, and all those losses can be included in a simulation model by simplified approach or by advanced approach, which is also included in our simulation tool AVL Exit. Other group of losses coming from the oil, so coming from the lubrication fluid in transmission, and those losses also can be simulated and accurately predicted using classical CFD methods. Finally, all losses can be summed up and in friction maps, and those maps can be used later on in system simulations for overall vehicle efficiency and COD emission prediction. The classical approach to consider friction in gear mesh is based on predefined and friction coefficients. So to go beyond this classical approach, so we introduced in this multi-body simulation also simplified electrodynamic lubrication theory and mathematical model behind, which considers simultaneously during whole simulation lubricant viscosity, lubricant entering and curvature situation on the gear flanks, and also flank surface roughness. So the results of this mathematical model is continuously and accumulated friction loss, which of course depends about local contact conditions in gears, like it is listed here. When you look distribution of normal forces along the gear flank, and also because changing of sign of sliding velocity, also considering of friction forces which are generated locally in this contact model. The next characteristic group of mechanical friction losses in transmission is or components which generate mechanical friction losses are roller bearings, which are widely used in transmissions. So we implemented our own numerical model for different types of roller bearings, like ball bearings, cylindrical roller bearings, needle bearings, and tapered bearings, and especially for prediction of friction generated by those roller bearings. So we introduced two approaches. So one is a classical approach where friction torque generated by bearing considers classical approach where this is divided in load dependent, speed dependent, and constant part of friction torque. And also we implemented also recent friction model coming from SKF, where friction model considers also rolling resistance, slider resistance, drag losses due to sealing, and drag losses due to oil drag. To be open with a software tool for the tools which are commonly used in concept phase, we also developed interface for Keysoft and Keysif, where those models can be included in our simulation tool and used as an input for further detailed multi-body dynamic simulation. There is also implemented interface to second standard design tool coming from Schaeffler Technologies Corporation, which is commonly known as bearings maps, where those results from this calculation, detailed calculation, can be included in our solution by exported lookup tables. For the other transmission components which are mentioned before, so we have also dedicated mathematical models which also beside other targets simulate also friction which is generated in those components. So, for example, for the clutch, we developed a special elastoplastic friction model for clutches, where we can simulate transient phenomena during engagement or disengagement of clutch plates, including also considering complex stick-slip effects where we have during these transition periods. Especially for open wet, for wet clutches, we included in the simulation model calculation of drag torques, which is generated by when wet clutch is open, And this model is in principle based on the standard two-phase friction model of wet clutch, but on the same time extended to also to consider heat balance in during oil flow between clutch plates. Another classical component which we are also considering in prediction of and simulation of friction inside transmission are also sealing losses, where we included and in a numerical solution also one analytical approach to calculate mechanical losses from rubber type lip sealing, which takes into account the main essential influences relevant for the friction, like sealing radius, radial sealing penetration or in pretension, lubricant viscosity, and of course surface roughness. The second group, which is I mentioned before, are hydrodynamic losses. So hydrodynamic losses coming from drag losses due to oil charging, and for simulation of such of those hydrodynamic losses, we are using classical CFD approach, where we are considering in those detailed multi-phase simulation rotational speed of gears, oil temperature, oil level, oil properties like viscosity, gear size, and of course other geometrical influences. So the approach is well validated and gives very accurate results comparing to the measurements. In our portfolio for hydrodynamic losses, we are using two approaches. So one is based on our tool, which is available on the market. So called this tool is called AVL Fire, and it is a standard 3D computation CFD code. Where we for simulation of transmission hydrodynamic losses using the multi-phase approach, which offers very accurate prediction of those losses. So as you can see on the left, we show this then a volume fraction between oil. So fluid phase and air phase as a fraction of oil missed in the gear in transmission or open volume. As a part of our simulation portfolio, we also we are also exclusive worldwide distributor for tool called Prion lamp, coming from the company 52, which use another CFD method called smooth particle hydrodynamics, which has advantages in CPU time needed for solving and in preparation of a model, as this numerical model doesn't need mesh preparation. Results from both approaches are in principle oil distribution, which can be used for improving of oil flow inside transmission, drag torques, shear stresses between oil and rotating components, and pressure forces. Finally, we are combining all numerical models used for prediction of mechanical losses, which are part of software solution, together with pre-calculated hydrodynamic losses, and we are applying those losses to final multi-body dynamic model, which was also presented before by Christoph, to get accurate prediction of needed for both for the rattle noise prediction and also gear whine noise prediction. As a part of multi-body dynamic results, we are getting also friction maps, which are then can be used further in simulation on the system level. Those friction maps can be then calculated for different operational conditions, different speeds, different loading conditions, and exported as lookup tables for further simulation, not just for the driving cycle simulation and needed for efficiency and fuel consumption prediction, but also for simulation tools which are dedicated for thermal management simulation, and also as a part of application area. Once when we calculated in detail all power losses inside the powertrain, so inside the engine, inside the transmission, so we can include these losses in a system model. So in this case, in our simulation portfolio, we are using AVL Cruise for such simulation. So the friction losses can be then included in the simulation model, like illustrated here, for example, for engine, as a single components, so that we can investigate for different operation conditions. So what is which group of characteristic losses is dominant, and what is the contribution of those losses, or can be summed up, like illustrated here for friction losses for transmission, where we complete transmission considered as one single object in this simulation tool. As a result from this calculation, so we are getting energy distribution where during a driving cycle, which can be predefined or real driving cycle, like we will illustrate in continuation of this presentation. This what is showed here is a classical approach where system model is offline model and simulation are done as steady state, and only longitudinal dynamic of vehicle is considered in this simulation. Our development now goes in more complex direction, so that we can couple this kind of offline model also with model which considers full vehicle dynamic, and based on this dynamic all driving conditions beside longitudinal acceleration, also lateral and vertical dynamics is considered. And this can be simulated with a software tool which is dedicated for this. In this case, what we are showing here is AVL Vehicle Simulation Manager, VSCM, which works together, and simulation are there together as one couplet simulation, so online coupling. And this coupling is done with a special tool produced by AVL, which is called also Model Connect. So this tool offers coupling of different simulation models in one co-simulation platform, which is then can include all possible effects important for prediction of real driving emission. What is our final target? So how it works? The coupling between different tools is not limited just for the simulation methodology, so simulation tools. So we can couple also hardware with and put the hardware in simulation loop. And in this case, we will demonstrate how this coupling is done by to include human, so driver in the simulation model in real time. Even if this is a simple approach, like showed here on the right top illustration, where we in the office have just a steering wheel and throttle pedal, or if this driver simulation is really complex, like in Hexapod showed also on this slide. This kind of simulation then can be used also for prediction of driving performance and fuel consumption, energy management and efficiency improvement, drivability prediction of a vehicle, and development of automotive AD or ADS functional development. Automatic driving assistance or full automatic driving condition. So how this coupling coupling approach can be used? So here for the illustration, so we coupled four different simulation tools, and also together with interface to real human driver which drives this simulation model. The vehicle dynamics is simulated with AVL VSM model, where a full dynamic of vehicle is considered, including road to tire contact, suspension forces, road profile, etc. The driveline model is created in AVL Cruise, where different components of drivetrain are modeled with specific elements. As we are using, in this case, also real-time engine model, so we developed also special tools called AVL Cruise, where you can specify build up engine model, which can also then work in a real-time environment. As we have in this case showcased also automatic transmission model. So we also included in the simulation model gear shifting model control, which is done in Simulink, and also control for clutch engagement and disengagement. Finally, we have interface to the steering wheel, which is in this case standard Logitech gaming hardware, which is connected with the simulation environment using USB interface and Python interface. All this then give us possibility to analyze real driving conditions, and as our co-simulation platform offers that all these coupled tools working together, so different channels are exchanged between the different tools, and we can also customize visualization of all these results, like showed here in the VSM environment. As the final results of this simulation, so we recorded for this use case driving profile for 12 different drivers, and which have different driving behavior. And we can see interesting things in this case. So each driver has different behavior, and the most defensive driver, we have two most defensive driver with the lowest average vehicle velocity. But in the terms of fuel consumption, the one driver has a superior achievement. So it achieved 37% of fuel consumption reduction in comparing with the same driver with different driving style, which has the same average speed. On the same time, we can see that the driver who has the maximum fuel consumption, in this case, the driver number 11, didn't achieve the maximum average vehicle velocity, what means that he has one not preferable driving style, and with a lot of acceleration of the vehicle and a lot of braking during this given route, which is predefined. So that was all from my side, what I wanted to show for this moment. we will go now with the question and answer session.
Thank you very much, Borislav. And for if you folks would like to send in additional questions, you can contact us at astmarketing@avl.com. We're going to turn now to our assistant, Thomas Resch of AVL, to take a look at some of these questions. We'll be answering questions until the top of the hour, so we have about 5 minutes. Please go ahead, Thomas.
Yeah, hello. We have several questions which arrived. Mostly it's regarding the NVH. So Christoph, one question is quite a good one, I would say. So for the gear wine optimization, typically you do this by profile modifications and corrections. But this is typically based for one, let's say, load condition. So how do you optimize this for a wider torque range, or how can this be done?
So we have a possibility to connect our software, also the optimizer tool, and we have for sure to have a look on different torque levels and finding the best trade-off using the optimizing or DOE tools on that. Currently, this is quite an important topic, as with upcoming regulations for trucks, bypass noises, they need to run on higher torque levels. So basically, the optimization of the best or less whine noise point needs to be redone with different noise levels. But basically, we have to focus on the entire operating range. Okay,
but for sure it can be only then for, let's say, for the most critical, it can be a balance.
It only can be a balance between the most critical and the other ones, for sure. But
we have.
Sorry.
Sorry, please. Yeah.
The best trade-off, we have to consider a wide range of torque loads. Yeah.
Okay, thanks. Then we had several questions on the material. So this means, especially also when you're using the gears plastic material, so does this have can you consider that? Can you consider it at all? And do you see effect on the gear rattle or the gear whine?
Yes, we can consider plastic materials. Basically, it's changing the stiffness in the contact models as well in the FM models. That's one point. So this has a directly impact on the gear whine excitation, on the stiffness variation, and on the other hand, for sure, the plastics has totally different damping compared with steel materials. Any kind of steel is almost very similar, let's say, but the big difference to the plastic is for sure the damping, and this can be covered within the model as well as in the combined model in these flexible gear models where we directly incorporate the gear wheel body as a FEM body, so this can be directly considered.
So this means the damping will have an influence mainly on the rattle and the stiffness then on the whine. So this means the material in both cases, for both main, let's say, NVH effects, has an influence, especially when it's going into plastic material. Exactly. Is this correct?
Yes, exactly.
Okay.
Okay, well, thank you very much. Okay. I'm afraid we're out of time, gentlemen. But it was an excellent presentation today, and we thank all of the attendees, those of you that have given your time to come and join us here today. We will be offering a recording of this event as a video because of the complexity of the slides. We're not sending out a slide deck, but we will have a video available, and you'll be receiving an email about that follow-up information. So Borislav Karlin, Christoph Schweiger of AVL, we thank you on behalf of Gear Technology Magazine, and we wish everybody a great day. Thank you for attending.